Good morning, sir.
Very good morning, ma'am. Very good morning, all. I welcome Dr. Kshitija Kadam, ma'am, for her second lecture on gauge under AICT Prerna scheme. Ma'am, I request you to please take over the session.
Thank you, sir. Thank you. Good morning, students. Let's start the topic. Uh, in last class, we have studied that if there is a beam, the beam will have shear force as well as bending stress. So, if the beam has shear force, some shear stress will come, and similarly, if the beam has bending moment, some stress because of this bending moment will occur. So one by one, we will see both the types of stresses in the beam. First, we are seeing bending stresses. So if beam is under bending, there will be two types of stresses: compressive stress and tensile stress. And both the stresses will be on a single section. For example, this is one of the beam, and if this is a beam, loading is given in the sketch, so accordingly there will be shear force and bending moment. Okay, so if there is bending moment, what will happen? The beam will try to bend. Take example of this sketch which is on right hand side. There is a beam having one support at left corner and other support in the middle portion in the right side. Okay, so in this beam, when it is loaded with some loading, here I have shown you uniformly distributed load. Consider any section A. If you consider this section A, and if you try to visualize the deflected shape of the beam, you will find that here it will deflect like sagging. In the middle portion of the span, the beam will deflect like sagging. Sagging, in last class you have understood, it is deflection like smile of shape of the smile. So the top fiber in section A will go in compression, whereas at bottom edge, bottom fiber, that fiber will be in tension. Here I have written, in section A, top fiber will be in compression and bottom fiber will be in tension. Take another section B. Here also it will deflect like sagging. So top fiber will be in compression and bottom fiber will be in tension. Let us take another section C, which is the rightmost end of this. And let us say this cantilever portion, overhang portion is very large. What will happen to this portion, this overhang portion? The beam will deflect in hogging shape. That means in the bottom you can see I have written in section C, the top fiber will be in tension and bottom fiber will be in compression. In short, we have understood that at a section from top to bottom, the stress pattern changes from either compression to tension or tension to compression. In all the three sections which we have seen in the sketch, in section A, topmost was compression, bottommost was in tension. So across the thickness of the beam, if we move, the type of stress changes from compression to tension. That means in between the top and bottom fiber, there will lie something which is called as neutral axis. What is this neutral axis? It is the layer in the beam which is neither in tension nor in compression, is known as neutral layer. This entire layer will be called as neutral layer. If beam thickness is ignored or beam width is ignored, the neutral layer, I should write here, beam width is ignored, then the neutral layer will become neutral axis. So within the thickness of beam, there lies some neutral axis at which the beam is not in tension, not in compression, and therefore its name is neutral. No tension, no compression, neutral axis. Okay. Then we can use lot of formula, lot of calculation, and that derivation I am not taking here. In finally, I am giving you this formula, the formula which is written in box, this formula. What is this formula? M stands for bending moment divided by I stands for moment of inertia, is equal to F. F is stress caused by the bending of beam. So it is called as bending stress, divided by Y. Y is the distance of particular fiber from neutral axis. So if I want to find out bending stress at a particular fiber, I have to take its distance y from the neutral axis, equal to E is Young's modulus divided by R, which is radius of curvature of the deflected beam. So this formula which is written in this box is very important, and to remember this formula I will give you small trick. The sentence I will utter will have first letter like this. You can see most important for your exam result. So this formula is very important, and we will use this formula to solve problems of bending stresses caused in beam because of bending. Okay. Then let us see one thing which is important here is sectional modulus. What is section modulus? We have already studied this formula, M upon I is equal to F upon Y is equal to E by R. Right? In this formula, if I write this first two things, first equation, and if I take Y on the opposite side, I will write bending stress is equal to moment upon moment of inertia multiplied by y. So here what we have seen in this equation, that stress is proportional to y. So y, what is y? Y is the distance of concerned fiber from neutral axis. तो हम न्यूट्रल एक्सिस से जितना दूर दूर जाएंगे स्ट्रेस की वैल्यू बढ़ती जाएगी. यहाँ पे y की वैल्यू कुछ थी तो स्ट्रेस की वैल्यू f थी. If I increase the value of y, the stress will increase. What I am understanding here, that at neutral axis stress will be 0, because at neutral axis y will be 0. And as we move away from neutral axis, the value of stress increases. That means the stress diagram is triangular. And on one side it will be tensile, on other side it will be compressive. So this M upon I, which is constant for that particular section, can be written as sectional modulus, and it is represented by Z. What is sectional modulus? If I want to write the formula, moment of inertia of cross section about neutral axis divided by the distance of the farthest fiber from neutral axis. Right? So using this we can solve few questions. I'm giving you a very small question here. Just quickly go through this because it is just like 2 marks question. A cast iron cantilever of length 1.5 meter fails when a load of 1920 Newton is applied at free end, and determine the stress in the failure, stress at the failure. The cross section of cantilever is given 40 mm by 60 mm. So it is under bending. So I will use the formula M upon I is equal to F upon Y. F has to be calculated. I, since this cross section is rectangle, we have already known moment of inertia for rectangular section in engineering mechanics. It is BD cube by 12. What will be Y? Y will be the maximum distance of fiber from neutral axis. So the maximum distance of fiber will be half of thickness. Thickness is given in the question 60. So 60 by 2 will be Y. And how much will be maximum bending moment? In the question it is written that it is cantilever. So if cantilever, we know that the maximum bending moment occurs at subfixed support. And the formula will be value of force multiplied by distance. So I know everything in my formula. I will just substitute and get the value of F. So in the question, directly bending moment may not be given. You may be given with the beam with loading. You have to find out how much is maximum bending moment, right? Let us move. You already know the assumptions. That the assumptions are mostly not asked, so that I will not take another example. The steel plate is bent into a circular arc of radius 10 meter. That means capital R is given. If the plate has cross section 120 mm wide and 20 mm thick, find the maximum stress induced in the beam and bending moment which produce the maximum stress is equal to E into 10 raised to power 2 into 10 raised to power 5 mm Newton per mm. So again we will use the same formula. In this, value of I is can be calculated easily because the beam is rectangular with rectangular cross section and the cross section in detail is shown in right side of the sketch. So I have calculated I, it is BD cube by 12. Always remember that cube of which value I have to take, which is perpendicular to the neutral axis. Because section is rectangle, so one dimension will be B, other dimension will be D. Which will be D, which will be cubed, is the dimension which is perpendicular to neutral axis. So here neutral axis is horizontal and 20 is vertical, so 20 cube. So I have calculated Y will be half of the thickness, maximum Y will be half of the thickness, so it is 10. E and R is given in the question. So using this equation, we will find out how much will be maximum stress and how much will be the moment. Right? Now, let us understand few things. What we have to understand? That on any section of the beam, the bending stress diagram will be a triangular diagram. Let us say the upper portion is in compression and lower portion is in tension. So all these stresses on upper portion above neutral axis are compressive stresses, and all these below neutral axis are tensile stresses. So stress can be converted into force multiplied using multiplication of area. So all these stresses will cause a compressive stress T, a compressive force C, and all these tensile stresses will cause tensile force T. And this C has to be equal to T because the beam is in equilibrium. The beam section is there only. So it is in equilibrium. So whatever is the horizontal force C, same will be horizontal force T. So if your cross section of beam is this arbitrary shape shown by the first sketch, or the cross section of beam can be this arbitrary shape which has more area at the bottom as compared to upper area, or the cross section can be I section, or cross section can be a rectangle. Whatever is the cross section, the important thing is C has to be equal to T. What does it mean? It means that neutral axis will lie on centroidal axis of the beam. This is important thing. Neutral axis will lie on centroid of the beam. So how to find out neutral axis? Just find out the centroid. Take this example. This is an arbitrary shape cross section of the beam, and you can see more portion is at bottom. So the centroid will lie below half of the height of the beam. So if centroid is here, the same will be neutral axis, and the bending stress diagram will be triangular. So you can see that the maximum stress at bottom is less as compared to maximum stress at top. So which one will be maximum stress at the top or at bottom will depend upon location of centroid. Take another sketch on right side. The cross section is in such a way that more area is on upper side. So centroid is at more than half of the depth, and at centroid there is neutral axis, and triangular stress diagram will show that maximum stress is at bottommost fiber as compared to topmost fiber. Third example, at the bottom you see, if it is a rectangular cross section, centroid will lie on the axis of symmetry exactly at half height, and in that case the topmost fiber and the bottommost fiber will observe same bending stress. So what I wanted to explain you here, that it is not necessary that topmost and bottommost fiber will have equal stresses. One more thing let us understand. Let us take an example of this cantilever beam, and a point load is applied at free end. So the beam will have bending moment diagram like this inclined line. Okay. Now we have this formula m upon I is equal to f upon y is equal to E by R. So you understand here two, three things, that I am interested in finding stress. So on what quantity stress depends? Mostly Young's modulus is constant and moment of inertia of the section is constant. Why? Because section is constant throughout the length of beam. So what are the other things remaining? Stress is proportional to M, which is bending moment. And second thing, stress is proportional to Y, which is distance of fiber, required fiber from neutral axis. So in this sketch you see, at free end bending moment is 0. So value of bending stress across the thickness is 0. Whereas if you see this another location, at this location there is some bending moment. So shear bending stress diagram is inclined triangular shape with small values at maximum top and bottommost fiber. As we move towards left, if I consider the leftmost location, which is the support, which observe the maximum bending moment, here you will find the bending stress diagram is most steep, most inclined. Initially at free end no moment at all, so no stress at all. As we move towards left, bending moment is increasing, so the ordinate of bending stress diagram is also increasing. Few points I can explain here. We are not going to solve a complete question, but if this type of question is there and you have to find out bending stress diagram. To locate bending stress diagram, we have to first locate the neutral axis. So our general formula for neutral axis location of centroid, because neutral axis lies on centroid. So let us locate the centroid first. This is the formula which you have studied in engineering mechanics. So we will use the same formula here. And here in this formula, we are calculating y from the bottom. This cross section has three parts: upper flange, web, and bottom flange. So I have considered these three as three different areas. So my formula is A1 Y1 plus A2 Y2 plus A3 Y3 upon A1 plus A2 plus A3. So it is simple calculation and we can substitute the values here, and we have calculated y bar, which is the location of neutral axis. It is 48.21 mm from bottom. So we first locate the neutral axis. In the sketch, I have located the neutral axis now. Now we will find other values in the formula. So I have to calculate I, which is moment of inertia of section about neutral axis. So again, using parallel axis theorem, we can easily find out that this is the part of engineering mechanics which you have already studied. Then one thing we have understood, that the given I section which is given in the question has bottom flange very heavy as compared to top flange. So obviously the neutral axis will lie in the lower region. It will not be at the half height of the uh, I section. So you understand that neutral axis is in lower section. So the bending stress at top and bottom fiber will not be equal. For those top and bottom, value of y will be different. You can see here I have calculated maximum y for top fiber is different and maximum y from bottom fiber is different. This is the maximum y from bottom fiber, which is nothing but the y bar of neutral axis. And total height minus that value gives you y maximum for top fiber. So in this formula, we will substitute the things, and then the bending stress diagram will be like this. The neutral axis is not lying in at half of the height. So you will find the bending stress diagram, which is triangular, has large compressive stress at top and small tensile stress at bottom. The formula is same. Only thing is y top will be applied to find out stress at top, and y bottom will be used to find out stress at bottom. It is simply supported beam, so top fiber will be in compression and bottom fiber will be in tension. So in short, we have only one formula for this all these problems, which is m upon I. This is another question. I will not go in much details in this question. The only thing is calculating I and calculating Y is only difficult thing. If it is hollow section, in engineering mechanics you have studied how to calculate moment of inertia about neutral axis, about centroidal axis for a circular cross section. And if it is hollow, it will be minus of removed portion. So we will move further. Let us understand few more things. Let us say that there is a horizontal rod, and if I am applying a force P like this, what will happen? The entire rod will increase. The length of entire rod will increase. So if I draw a stress diagram across the thickness, you will find that the entire rod is in tension, so the same stress diagram is observed. And the formula for stress will be P upon A, the force applied upon cross section area. Take another example. That same rod is there. Now I am applying a compressive force like this. So entire cross section will observe change in the length. The length will reduce and the stress diagram will be compressive, and the formula will be same, F is equal to P by A. Now take third example. Same is my rod, but this time I am applying a transverse load. Transverse means load perpendicular to the axis. So what will happen? The uh, the beam is bending and the top fiber will observe compression, bottom fiber will observe tension. Since top and bottom fibers are observing different type of stress pattern, the stress diagram will be triangular like this, showing zero value at neutral axis. So for this, for calculating stress, I have different formula. For only axial problems, formula was P upon A. But for bending, formula is M upon I is equal to M upon I multiplied by Y. So the rod is same, only the way of loading is changed and the values changes. The formula changes. Okay. Take fourth example. Here, the same rod is there. This time I am again pulling it. I am applying force P on both the sides. But this time I am putting my force at some eccentricity E from neutral axis. And I have to find out how much will be stress. So what your common sense says, will length of beam will increase only, or will it bend also? I am having this large value of E. So you can visualize that the beam will, the rod will deflect like increase in length as well as hogging, because this is not, the force is not applied at neutral axis, it is applied at some distance. So what will happen? I can translate my given problem into the problem which is shown in next sketch below, just below that it will observe a axial pull P, and it will also observe a moment which will be equal to P multiplied by eccentricity E. So now this time the rod is subjected to two types of things. First is axial pull, which will cause stress diagram in which entire thickness will increase and the constant tensile stress diagram will be observed. You can see the first stress diagram is because of pull P. And second, moment is also observed. So that moment will give you bending stress and which will be inclined. So the final force F will be summation of these two. So what I want to explain you here, that it is not necessary that axial if I am pulling it, only length will change. If I am pulling it along the neutral axis, length will change. If I am pulling the rod with some eccentricity from neutral axis, the rod will observe expansion as well as bend. So understand that it is not necessary that your problem will have only if you are pulling, only axial will happen. No, you have to understand the behavior, how it is deflecting, and accordingly you have to use the formula to find out stresses. Here I am taking a question in which there is a beam of cross section as T beam, and it is applied with a pull P, which is located at 50° from bottom. So I will not simply say that the length of beam will increase and the stress will be only because of pull. which is P upon A, force upon cross section area. I have to check whether this force P is applied on neutral axis or not. So what I will do, for this T cross section, I will first find out the neutral axis. If I calculate the neutral axis using the simple formula of Engieering mechanics, I have calculated that neutral axis lies at 100 mm from bottom. So here is the trick of the question, that neutral axis is located at 100 mm from bottom, whereas the force P given in the question is located at 50 mm from bottom. That means force P is applied with eccentricity. So if force P is applied with eccentricity, here you can see the sketch. This is T cross section. The neutral axis is located at 100 mm. You can see in the sketch I have drawn a line by dot dash. It is neutral axis, but the P is located not on neutral axis. In the sketch you can see P is located at some eccentricity. And how much that eccentricity is 100 minus 50. So the beam will observe axial force because of P as well as bending because of moment. And how much will be moment? P into E. Okay. Now you can see, and summation of these two stresses will give you total stress diagram. Right. Now you visualize the entire beam. This is beam, and which is having a neutral axis which is shown by dash dot line. And P is applied at the bottom of that. So you will observe that the top fiber will observe compression and bottom fiber will observe tension. So when I have to find out total stress at bottom fiber, I will write stress because of P, which is tensile, and stress because of moment, which is also tensile. So I am adding these two. And similarly, at top fiber, pull will give expansion, but moment will cause compression. So I am deducting them, and that will be minimum stress. At bottom fiber will be maximum stress, and at top fiber will be minimum stress. With this example, what I want to convey, that whatever is given in the question, please visualize your question properly. Visualize the question properly and then apply the formulae. You as an engineer should be able to visualize how the structure is deflecting and what is its deflected pattern. Okay, so this is something about bending stresses which we have seen till now. Now let us go for other type of stresses. Here I have written there are two types of stresses in beam. First is bending stress. For that I have given you the formula. M upon I is equal to F upon Y is equal to E by R. Now let us study the second type of stresses. It is shear stress. And the formula is Q is equal to SAY bar upon IB. What is Q? Here I have written everything about it. What is Q? Q is shear stress at a fiber. So you understand again, just like bending stress, the value of Q varies from across the thickness. So fiber to fiber we have to calculate it. So Q is shear stress at a fiber. Capital S is shear force at that section of the beam. AY bar is moment of area beyond the fiber above the fiber where Q is being calculated. I will explain this in sketch, but you just understand that AY bar is moment of area. That means moment multiplied by distance from neutral axis. I is the moment of inertia of the cross section area of entire cross section area of the beam about neutral axis. And small letter b is width of the beam at a fiber where Q is being calculated. Okay, let us understand few things. Let us say this is my beam which is supported on left and right corner, and it is loaded with some load. So this beam will have number of layers in it, and when you load it, it will deflect like this. Due to bending, the top fiber will observe compression and bottom fiber will observe tension. Due to this, layers in the beam will slide over each other. You take an example. You take a thick book in your hand. Since we are learning this topic of online, so you take this, you do this experiment at your home. Hold a thick book in your hand and try to bend it. You will observe that pages of book slide over each other while bending. So the book is in the book, pages are not glued to each other. So when you try to bend, the pages slide. But in case of beams, it is a monolithic thing. So the pages or the layers cannot slide. So these layers will offer shear. And because of that shear, when movement is not allowed, it will offer some shear stress. And that shear stress is Q, which is equal to SAY bar upon I. So understood why bending causes shear? Now let us understand the formula properly. The formula is Q is equal to SAY bar upon IB. S we have understood that it is shear force on the section. I is the moment of inertia of entire cross section. What is B? What is AY bar? That let us understand using this sketch. Let us say this is some cross section of beam and it has a neutral axis which is shown by a dashed dot line. Now with this arrow I am telling you this is the fiber where shear stress has to be calculated. This is the fiber. So AY bar is moment of this area which is above this fiber, which is shown by this shading. So AY bar is moment of shaded area about neutral axis. And this small letter b is width of the fiber. So this distance will be b. So this is the way we will use the formula. Now, let us use this formula and understand the formula in better way. And let us find out few ready-made formula which will be used for Viva or MCQs. Shear stress diagram for a beam with rectangular cross section. Here in the sketch I have shown a beam with rectangular cross section having width B and depth D. Now let us say I have to find out shear stress at EF. So the formula is already known to you. S will be the shear force at a section. AY bar, it is moment of area above that fiber. So above EF, I have shown the area with shading. So I have to find out moment of this shaded area about neutral axis. So you can see it is moment of area. So first I will write area, then multiplied by distance of neutral axis from the centroid of this shaded area. So how much is shaded area? Width will be B and depth will be depth of shaded area only. It will be D by 2 into Y. So in first rectangular bracket, it is area. And in second rectangular bracket, it will be distance of centroid of shaded area from neutral axis. So it will be D by 2 plus Y whole divided by 2. So I will simplify it. And moment of inertia of cross section area about neutral axis, it is a rectangular cross section, so it is BD cube by 12. And in formula, the B will be the same value B because the cross section is having constant width B. So let us substitute all these things in the formula. This will be the formula. I am moving my cursor. This will be the formula for bending stress for a rectangular section. Here you understand two, three things. The value of shear stress Q depends upon Y. And that means it is not constant across the thickness. Second thing, it depends upon Y square. That means the variation of shear stress across the thickness will be second degree, parabolic. Third thing you understand that we have to calculate the shear stress across the thickness one by one. So let us first find out at top fiber. Shear stress value of Y will be D by 2 at the topmost fiber. Y will be D by 2. We'll substitute here. So Q at top comes out to be 0. At middle, that means on neutral axis, Y will be 0. So shear stress we have calculated as 6S by 4 BD. And at bottom, Y will be minus D by 2. So shear stress comes out to be 0. Here we have to understand one more thing, that Q depends upon Y square. So if fiber is above neutral axis, it has Y positive, and if it is below neutral axis, Y is negative. But whether Y is positive and negative, it doesn't carry any meaning because I am taking square of that Y. So you understand the diagram will be little symmetrical about neutral axis for this rectangular area. So this will be the shear stress diagram across the thickness. You can say it is a second degree curve parabola. It has 0 values at top and bottom corner and maximum 3 by 2 S by BD at the neutral axis. And what is S by BD? S is the shear force, BD is the cross section area. So S by BD is average shear stress. If I don't know this variation, I will say shear stress is force upon area. So average shear stress is S upon BD. So here we can simply understand that for rectangular area, maximum Q is equal to 3 by 2 average Q, average shear stress. Similarly, I can find it out for circular section also. I am just telling you the final answer, that for circular shear stress diagram also the uh, shear stress diagram is parabolic and maximum shear stress is equal to 4 by 3 average shear stress. Let us take one example here. I have a cross section in the shape of T. Okay, and my aim is to draw shear stress diagram. So we can easily understand that at top fiber shear stress will be 0. Why? Because shear stress has formula S multiplied by AY bar upon IB, where AY bar is the moment of area above that section. So about topmost fiber, nothing is there. So AY bar for top fiber will be 0. So without doing any calculation, I know that at top fiber, shear stress is 0. Similarly, at bottom fiber, shear stress is 0. Why? Because in the formula, in the very first formula which I have given, A y bar is the moment of area beyond that fiber. I have said beyond that fiber. That doesn't mean above or below. So if I'm considering the lowest fiber, the area beyond it, below it is 0. So shear stress here will also be 0. One more point I want to explain you here, that at the junction of flange and web, at the junction of flange and web, how much value is somebody saying something? At the junction of web and flange, I have to understand properly that the formula is same. The formula is S A y bar upon IB. But this value of B should be taken how much? At the junction of web and flange. At the junction of web and flange, this B has to be taken as 200 or as 50. So at the junction where there is sudden change in width of the section, the shear stress has to be calculated twice. Here I have calculated Q for flange and Q for web. Both these Qs are for the junction of web and flange. So you can see in the diagram, there is sudden change in stress diagram. Because the formula says that shear stress is inversely proportional to B. So in flange, B is large, so shear stress is less. In flange, B is very small, so shear stress is suddenly increased at the junction. So using this concept, we can say that yes, shear stress diagram will be like this for these shapes. If I have a rhombus shape of cross section, see the second row, the shear stress diagram will be like capital letter B. At the neutral axis, at the centroidal axis, Q will be equal to average Q, and at particular height it will be 9/8 average Q. For I section also you will find it is parabolic, but since the width suddenly changes from top flange to web, there is sudden increase in the shear stress diagram. At the junction of web and bottom flange, suddenly B is increasing, so shear stress is suddenly reducing. And same example you can see in bottom sketches also. If you see the bottom left sketch, initially the width is less, so the stress diagram is more. Suddenly at the bottom of this groove, width has been increased, so the shear stress decreases. So the shape of shear stress diagram can be visualized using the shape, observing the shape of cross section of the beam. Right. Then let us go to the one thing which is in your syllabus, which is shear center. So first understand, what are the types of bending? There are two types of bending. symmetrical bending and unsymmetrical bending. This is a sketch I have shown here. It is a beam which is bent, and on right side you can see the cross section of beam. I have shown with dash dot line the neutral axis and the vertical symmetrical axis. So a beam will observe symmetrical bending when the load line coincides with principal axis of section. What do you understand by principal axis? You have already studied in engineering mechanics about principal axis. In short, I will tell you, if section is symmetrical, principal axis coincide with symmetric axis. So in this example, I have cross section rectangle which has a horizontal and a vertical axis of symmetry. And in this sketch, the load line, the direction of load is matching with the vertical symmetrical axis. In cross section also you can see, and in bend beam also you can see that all the loads are applied on that symmetrical axis which is shown by dash dot. So if load line coincide with principal axis, the beam will observe symmetrical bending. Whereas the beam will observe unsymmetrical bending when, here there are two situations. Either the load line is oblique with symmetrical axis of the section. What does it mean? Section is symmetrical, that is, it is rectangle or I section or circular. The section is symmetrical, but the load line is oblique. Oblique का क्या मतलब है कि आपकी ऐसी एक बीम है और उस पे लोड ऐसा लगा है कि जो बीम को ट्विस्ट करने की कोशिश कर रहा है. यानी आप एग्जांपल लो कि मम्मी जब कपड़े सुखाती तो एक हाथ कपड़े निचोड़ती है, तो एक हाथ से एक कपड़ा पकड़ती है, दूसरे साइड से उसको ट्विस्ट करती है. तो वो ट्विस्ट में यदि लोड लाइन टेढ़ी लगी है तो ही ट्विस्ट होता है. सो unsymmetrical bending is observed when load line is oblique with symmetrical axis of section. This is one of the case कि जब unsymmetrical bending हो. unsymmetrical bending का क्या मतलब होता है? Bend भी हो रहा है और twist भी हो रहा है. और second variety, when the load line is along centroidal axis but the section is not symmetrical. Section is L section or C section. That means the load line is matching with centroidal axis, but the section itself is not symmetrical. In these two cases, either or, what is result? Result is that the beam will twist along with bending. This thing is called an unsymmetrical bending. So take this example that this is a cantilever beam having C section. It has a C section. C section means the cross section is like capital letter C. In cross section you can see I have shown here dot which is centroid, and along that dot, along that centroid, vertical force P is applied. So force is applied along centroidal line, but section is not symmetrical. So in the sketch you can see the beam is twisting clockwise, right? So if beam has any of these cases, there can be unsymmetrical bending. That means the beam will bend, also it will twist. So if this is the case, this is not favorable thing. आपने बीम क्यों बनाई है कि वो बेंड हो, पर ये unnecessarily additionally twist भी हो रही है. So that has to be avoided. So how we avoid that? to avoid twisting of beam, concept of shear center is introduced. In this sketch I am explaining the same beam, same cantilever, but what I am doing here, in first sketch you see that the beam is twisting clockwise. So what I did, मैंने ये applied force P को थोड़ा सा उल्टी साइड में खसका दिया है. What it is doing? This, to avoid twisting, the applied force is placed on point O. This, when I have shifted this point, this force P from point centroid to point O, now this force P will try to move it anti-clockwise. So the cross section of beam is trying to rotate it clockwise, twist it clockwise. The applied force which is applied on point O will try to move it anti-clockwise, and hence the beam will not twist. It will only bend. So this point O is called as shear center. Let's see the definition of shear center. It is defined as a point on beam section on which, when applied force is placed, there will not be twisting in the beam. So this is the concept of shear center. You understand one more thing? If section is symmetrical, shear center will lie on centroid of the center section only. क्योंकि यदि सेक्शन सिमेट्रिकल है तो वो ट्विस्ट होगा ही नहीं. तो लोड लाइन जहां पे लगी हुई है वहीं पे वो जीरो ट्विस्ट दे रहा है. So shear center will coincide with centroid of the section. But if your section is C section, that is shown in the sketch, you can see the sketch, the cross section is given. The force P has to be applied at shear center, and the eccentricity of shear center will be calculated by this formula, where the small letter D is center to center depth, B is center to center width of the flange, T is thickness of flange, and I is, as usual, moment of inertia of the given section about neutral axis. Right? Let us move to some other concept. What is concept? That if we have this you have already studied in engineering mechanics, that if there is some force P, I can replace the force P to the same value of force in the same direction, but at some other point, not on the same line of action, along with some moment. How we can do this? This is applied force P and it is at some eccentricity from neutral axis. So what I will do? At neutral axis, I will apply two equal and opposite forces P. So these are two equal and opposite applied at the same point. So it is as good as the first sketch. Now the applied leftward P on neutral axis and original P towards right, these two will make a couple, because these are two equal and opposite forces at a distance E. So these two will make a couple which will have moment is equal to P into E, and one rightward force on centroid will remain as it is. So given force is converted into same force at some other location along with some moment. Okay, so this thing is used in case of direct and bending stresses in column. Take an example, there is a column and I am applying a compressive force on this column. So entire column will observe compression. So the column will be under pure compression, and the compressive stress diagram across the width of column will be constant. You see the first sketch. Force P is applied on the neutral axis. Entire column is compressing, and the compressive stress is constant. Let us see the second sketch. P is applied with some eccentricity with neutral axis. So the deflected column will, the length of beam column will reduce, as well as bending will happen. So you can see compressive force is there and bending is also there. And total stress distribution will be like this, adding these two quantities. If I increase the eccentricity, let us see the third sketch. If I increase the eccentricity, moment equal to P into E will increase. So if moment is increasing, you see the stress diagram for bending in third sketch is more steeper. If you compare second sketch and third sketch, the bending stress diagram is more steeper in third sketch. And you can observe that if I add compression because of force P and because of moment, if I add the final stress in third sketch, may have some tension in the column. Okay, so this is not good for columns. What is columns? Column is actually loaded uh, members. So the mostly the columns are subjected to compression, and the compressive stress formula will be P upon A. A is cross section, and the column will fail in crushing. This happens with short columns. But if I have long column, what will happen? When I am applying force P, the column will, the length of column will reduce. That means compression will happen, but it will start buckling like this. The long column will buckle when P is increased. The load at which columns just buckles is called as buckling load. So in that situation, what will happen? There will be total stress because of axial compression and because of bending. But stress because of bending will be triangular. So it will be compressive as well as tensile. So when I have to calculate maximum stress, I have to take compressive compression and compressive bending. And to find out minimum stress, I have to take compressive compression and tensile bending. And how much will be moment in the bending? Moment in the bending will be P into E. I am finding the stress at the middle of the section. The section is here. Initially it was vertical column, but because of buckling, section has moved. So on the central section, the eccentricity is P into E. So the moment is P into E. So if long columns are there, the column will fail because of buckling. Here you can see when P reaches to maximum, the column will fail due to compression as well as buckling. But if the column is very long, if column is very long, the axial compression will be very small as compared to bending. Bending means buckling. So the column will, so for very long columns, failure is mainly due to buckling, not due to compression. This is Euler's theory that for very long columns, failure is mainly due to buckling. And this buckling load, which is the load at which column starts buckling, depends upon the boundaries condition, the support conditions of the column. So if both the ends are simply supported, The buckling stress buckling load is like this. If one second sketch, one end is fixed, other is free, the buckling load is given. Similarly, third case, one end is fixed, both the ends are fixed, and fourth, one end is simply supported or hinged, one end is hinged and other is fixed. So if boundary conditions or support conditions are different, buckling loads are also different. You can see in the formula. Then a new concept is added, effective length. And you can see effective length for all these four cases, four types of supports are different. What is effective length? Let us understand properly here. In short, you understand effective length is the length which deflects from its original shape. So if both the ends are simply supported, the column will buckle like this dotted line. Entire length of column is buckling. So you can see that effective length capital L is equal to actual length small l. If both the ends are fixed, second case, if both the ends are fixed, at fixed support there is no slope. So initial portion will be vertical straight and then buckle, and again at top fixed support the slope will be 0. So only net half of the um, length is coming out from its original position. So we will say that effective length is half of its original length. Third variety, when one end is fixed and other end is simply supported. At simply support there will at hinge there will be slope, and at fixed support there will not be slope. So the deflected shape will be like this. So it will be, the effective length will be small l up under root 2. And the last case, when one end is free and other end is fixed, the column will deflect like vertical cantilever. And if I compare top line, top end, so at the bottom in the same vertical line, I have to imagine a horizontal, another dot point which is imaginary. So I have shown dotted, and total length is 2l. So for different uh, support conditions of column, the effective length is different, and calculation of effective length is not at all difficult. You can visualize and you can write. Now whether the column is long, short, how it will fail depends upon one quantity which is called as slenderness ratio, and it is nothing but the effective length of column divided by least radius of gyration. And the word radius of gyration is already known to you. In engineering mechanics, you have studied radius of gyration is under root moment of inertia about sorry, radius of gyration is equal to under root moment of inertia divided by cross section area. So this is about long columns. Now let us see about columns, and if they are not long. If they are not very long, so Euler's formula will not be applied. What is Euler's theory? Euler says that if the column is very, very long, it will deflect, it will fail only because of buckling. But if column is not too long, I have to consider compression as well as bending. So I have two formula. For compression, a formula is F is equal to P by A, and for bending, I have the formula most important for your exam result. And if both things are happening, I have to club these two, superimpose these two formula, and I have to find out final stresses. Okay. The same thing I am explaining here. if there are columns, generally they are expected to be good in compression. But why they are good in compression? That means generally tension in columns are avoided. So what is the condition for rectangular column to remain in compression completely? No tension will be observed. So let us take an example. Here I have shown a column and it has side A and side B. And a force P is applied vertically down with some eccentricity E from neutral axis. So applied load is applied with some eccentricity. That means the column will observe compression as well as bending. In the sketch you can see I have shown that because of compression P, constant compressive stress FA for axial I am writing FA is there. And since the P is applied with some eccentricity, a moment will occur and that moment will cause bending. So in the lowest diagram I have shown bending stress which is triangular. So if I combine these two types of stresses on section A, the total stress will be equal to FA, that means stress because of axial force plus stress because of bending. I am adding them because both are in compression. On edge B, on the left part B, you can see the total stress will be FA minus FB because FB is tensile, so it is with negative sign. Now, if FA is more than FB, the final stress will be positive. That means the side B will be in compression. But if FB is larger than FA, side B will be in tension, which is not acceptable most of the cases. So we have to think of this in details. To avoid tension on side B or anywhere in the column, the bending stress which is tensile in some location has to be at the most equal to compressive stress FA. So let us substitute the values. Axial stress is P upon A and bending stress is M upon I into Y. It is a rectangular cross section. So accordingly area and Young's model area and moment of inertia values and Y values are written here. Understand here, I am writing A B cube by 12. Why? Because in my sketch column is bending in this way and the B is the height of beam now. So it is AB cube upon 12. And if we solve this formula, the value of E eccentricity comes out to be B by 6. So if force P is eccentrically applied, E has to be less than and equal to B by 6 to avoid tension in column. यदि E की वैल्यू B by 6 हो गई तो एज साइड B पे स्ट्रेस 0 आएगा और यदि ये E से थोड़ा भी बढ़ गई ना तो वहां पे पॉजिटिव वहां पे टेंशन आने लगेगा. So E has to be less than equal to B by 6 to avoid tension in column. That is, force P has to be in middle 1/3 portion of the width of the column. So this thing is called as middle 1/3 rule, that if applied force is within 1/3 portion of the column will be in compression only. Okay, but the column cross section is not just surface. It is a 3D thing. Column is a 3D thing. So here in the sketch I am showing that it is a column having cross section A multiplied by B. This is vertical column and it has four corners at the bottom, capital A, capital B, capital C, and capital D is behind. And the column is subjected to force P, which has eccentricity x in x direction in the and in B direction and y in A direction. So I have to calculate stress. Now you understand that eccentricity is not only in B direction, it is also in A direction also. So the stress at four locations, capital A, capital B, capital C, capital D, will be different. By your common observation, you can see at point A, what will happen? The force P will give you compression, but moment in B direction will give tensile and moment in Y direction also will give tensile. So these two quantities are with negative sign, right? You can visualize. See students, I have one solid understanding of the subject that we engineers has to visualize our problem and then apply the formula. So you just visualize that force is applied somewhere here. So obviously these moments will try to pull up this point A. So the moments are with negative sign. Stress caused by moments are negative sign. Similarly, at point B, the compressive stress will be same, and force in B direction will give positive, that means compression. But eccentricity in Y direction will give negative, that means tensile stress. So with negative sign. At point C, both the moments will be positive. In the sketch, you can visualize this is point C. So force will give you compressive stress positive. Eccentricity in x direction will also give compressive stress, and eccentricity in y direction will also give compressive stress. And the last one, stress at point D, which is this point, will give compressive stress because of force, negative stress because of eccentricity x, and positive stress because of eccentricity y. So read the question carefully, draw the sketch, visualize the sketch, and then apply the formula. Now we have seen that if there is a rectangular cross section of the beam of the column, to avoid tension, it has to be, the force has to be in middle 1/3. So this is the width B. So middle 1/3 is the area where force can be applied. Similarly, this is depth A. So in middle 1/3 it has to be there. So you can see in the sketch I have shown a dotted rhombus portion. This is the dotted rhombus portion which satisfy 1/3 for A and B directions. So in this rhombus portion, if force is applied, the entire column will be in compression. This shaded rhombus portion is called as core of the section or kernel of the section. It is the area of cross section where if we apply force, the entire column will remain in compression. Similarly, I can derive core core for section for rectangular cross, for circular cross section. There also you can find if diameter of section is D, if I apply force, compressive force in the central D by 4 area, the column will be in compression. For any other area also we can find out. In this question, there is I section of column and the area, moment of inertia, everything is given. We have to find out what is the core or kernel of the section where I can apply force to keep the entire column in compression. So we have formula to avoid tension. Axial stress is equal to bending stress. Axial stress is P upon A is equal to bending stress because of eccentricity in x direction and because of eccentricity in y direction. So section modulus you have studied. So in short, in place of moment, I will write P into E in x direction, and in place of I by y, I can write zx. Similarly, for y direction, Pey upon y, zyy. So P will cancel out from all the three from this equation, and Pe and Py can be calculated, which is P eccentricity in x direction is 69. So you can see 69 is shown in vertical direction, and similarly Ey is 9.28. So this rhombus is this rhombus, no, this is not rhombus, it is parallelogram. This parallelogram is the core of the section. So to find out core of section, what is the formula? Axial stress is equal to bending stress. Axial will be compressive and bending can be tension. So if we equate them, I will get the maximum eccentricity allowed. So this is about direct and bending stress. Now we will go to the last topic allotted to me, which is torsion. So torsion, consider the rod and consider that it is made up of slices. यानी इसको ऐसे कंसिडर करो कि आपके पास बिस्किट का पैकेट है, गोल गोल बिस्किट, और वो पैकेट में है. अब इस पैकेट को मैंने एक साइड से फिक्स पकड़ लिया और दूसरे साइड से उसको रोटेट किया, तो ये बिस्किट सब एक दूसरे के ऊपर ऐसे स्लाइड होंगे ना. वो सारे बिस्किट का ऐसे लंबा पैकेट है, एक साइड से पकड़ लिया, दूसरे साइड से उसको हम टॉर्क लगा रहे हैं, उसको रोटेट करने की कोशिश कर रहे हैं, तो जो सारे बिस्किट है वो एक दूसरे के ऊपर स्लाइड होंगे. ये सारे बिस्किट्स अलग अलग हैं इसलिए ये स्लाइड होंगे, पर बीम में तो मोनोलिथिक है, तो बीम में स्लाइड अलाउ नहीं रहेगा, तो वहां पे shear आएगा. So the slides or the biscuits will slide over each other causing shear. So the torsion causes shear stress. यानी हम यहाँ पे टॉर्क लगा रहे हैं, टॉर्शन टॉर्शन ऑब्जर्व कर रहे हैं, पर अंदर मटेरियल में क्या हो रहा है? मटेरियल इज ऑब्जर्विंग shear stress. So the formula for this is Fs upon R is equal to Q upon small r is equal to C theta by L is equal to T upon IP. This is torsion formula. And what are the contents in this formula? Fs is shear stress at the radius R. Here in the sketch you can see radius is R. Q is, small letter q is shear stress at radius small r. That means you can understand, जो इसका न्यूट्रल एक्सिस है वहां पे स्ट्रेस कम रहेगा, जितना हम दूर दूर न्यूट्रल एक्सिस से दूर दूर आउटर मोस्ट फाइबर पे जाएंगे, shear stress की वैल्यू प्रोपोर्शनली बढ़ेगी. तो so therefore it is Fs upon R is equal to Q upon R. Fs is shear stress at outermost fiber, Q is shear stress at intermediate fiber of radius small r. C is modulus of elasticity. You have studied this modulus of elasticity. It relates shear stress upon shear strain. So you can observe torsion का हम क्वेश्चन पढ़ रहे हैं पर हम उसमें shear की प्रॉपर्टी यूज कर रहे हैं. Theta is twist angle, and in the formula theta has to be taken in radians. Be careful, not in degrees. What is theta? Theta is angle AOA dash. L is the length of rod. Phi is the shear strain. Phi is the shear strain. That means angle A. This angle on the left side, the angle which is created is shear strain. T is the torque applied, and IP is polar moment of inertia of cross section of the earth. Polar moment of inertia you have studied in engineering mechanics. It is moment of inertia perpendicular to the cross section. It is calculated using perpendicular axis theorem. Using this, let us try to understand few more things. Why a torque is applied on any rod? Torque is applied on any rod to transfer power using this shaft. In all the machines, in most of the machine you have seen there is a shaft. एक साइड इंजन लगा हुआ है, दूसरे साइड पे उसका मूवमेंट लगा हुआ है. तो हम उस पे टॉर्क दे उस shaft पे टॉर्क अप्लाई करते हैं तो दूसरे एंड पे भी ट्विस्ट मिलता है अपन को. सो power, how much is power transmitted by shaft? It is mean torque multiplied by area angle turn per second. पावर है तो पावर का यूनिट क्या होता है? एनर्जी अपॉन टाइम. तो एनर्जी कैसे निकाल रहे हैं अपन? टॉर्क मल्टीप्लाइड बाय ट्विस्ट इज एनर्जी पर सेकेंड इज per unit time. So if let us say n is rpm of the shaft which is moving, तो एंगल कितना हो गया? n रोटेशन पर मिनट. सो अपन को रोटेशन में नहीं चाहिए, वी रिक्वायर इट इन रेडियंस. So n into 2 pi divided by 60 seconds. Accordingly, I have substituted in the formula. Let us solve quickly one small problem. A solid shaft is subjected to a torque 15 kilonewton meter. Find the necessary diameter of torque if the allowable shear stress is 60 Newton per mm square and allowable twist is 1 degree in a length of 20 diameters of the shaft. Take C is equal to 8 into 10 raised to power 4 Newton per mm square. So I have this formula which is already explained to you. Let us substitute the quantities given in the question. T is already given in the question. IP for circular section it is pi r square, pi r 4 upon 2. R is given in the question. No, R has to be calculated in the question. C is given for twist it is given in terms of length. So 1 degree in 10 diameter length. So in place of length I have written 20d and in place of theta I have written 1 equal to, उन्होंने बोला है कि ज्यादा से ज्यादा shear stress 60 न्यूटन पर mm स्क्वायर हो सकता है, तो 60 अपॉन r. सो दो कंडीशन दिए हैं, मैक्सिमम shear कितना हो सकता है और मैक्सिमम ट्विस्ट कितना हो सकता है. And our aim is to find out r. So first we will consider twist criteria. We will take these first two parts of the equation. We will equate it and we will find out the value of r. And considering shear criteria, I will take first and the last part of the equation. I will equate them and I will calculate R is equal to 54.2. So in a single question, you can have two criteria. ज़्यादा से ज़्यादा shear कितना ले सकता है या ज़्यादा से ज़्यादा twist कितना हो सकता है. So using both the criteria, I have calculated R and the lowest R I have to finalize. Okay. So student, perhaps we are in with the topic as well as our time. I want you that since a very small time duration is given to me, I cannot completely satisfy your queries and I can give good tricks to you. The only one trick I want to explain you here, which is given to me by my one of teacher in IIT. He used to say one statement. I want to share that statement to you. He used to say, "Beta, see the structure and see through the structure. Solution lies there only." I am repeating, see the structure and see through the structure. Solution lies there only. Because our structures cannot tell us that what type of failure, what type of stress they are observing. Unlike medico doctors, when patient comes to medico doctors, the patient tells them that मेरा पेट दुख रहा है, मेरा सर दुख रहा है. The doctor has some clue what treatment he has to do. Whereas as engineers, we don't have any clue. Our structure don't tell us what is the cause of its distress. So our responsibility of engineer increases many fold. हमारी responsibility बहुत ज्यादा है. We have to see the structure and we have to answer. We have to judge कि क्या है हो रहा है उसमें, bending हो रहा है, shear हो रहा है, torsion हो रहा है, and accordingly we have to apply the formula. So in short, I want that as a civil engineer or as an engineer, you should visualize the behavior of problem and then only apply the formula. This is all from my side. Thank you, students. Thank you, sir.
Thank you very much, ma'am. Thank you very much for delivering such a wonderful lecture on simple engineering. Now I open this session for question answer. If you have any questions, students, please ask.
Or you can these students can write their difficulty on to me in WhatsApp. So you can share my number to these students if they have any issues. I can solve in WhatsApp also.
Okay, ma'am. Okay, ma'am. I definitely share your number and as well as your email ID on their WhatsApp group. So they can ask the question on their convenience. Okay, thank you for joining and delivering the lecture,
Thank you, sir.
ma'am. Thank you.
Thank you, sir. Thank you.
फाइनल ईयर से कौन कौन है यहाँ पर? ललित है, नेहा है, प्रणाली सोनकुसरे है, प्रियंका पौनीकर है. Don't leave the class, anybody. Don't leave the class. Only 9 to 10 students are there. I don't know what is priority to you. इतना खूबसूरत लेक्चर मैम ने लिया है और लास्ट टाइम भी मैम ने जो पढ़ाया है बहुत अच्छे से पढ़ाया है. ऐसा तो कोई है नहीं कि आपको बोर हो रहा होगा. कि दिक्कत क्या है? आपके लेक्चर तो है नहीं ना अभी. तो बाकी लोगों ने ग्रुप मतलब मीटिंग क्यों छोड़ा मेरे समझ में नहीं आ रहा. ना ऐसा तो नहीं कि मैंने वहां पर मैं अटेंडेंस पेस्ट किया और अटेंडेंस में उधर डाला और अपना निकल गए. तो मैंने मैसेज डाला है. जिन लोगों ने भी अटेंडेंस वो गूगल फॉर्म में भरा होगा सारों की अटेंडेंस डिलीट कर दिया मैंने. दे विल बी मार्क एज एब्सेंट. ओनली दिस 9 स्टूडेंट विल बी कंसिडर एज प्रेजेंट. मजाक लगा के रखा तुमने। वो 1.5-2 घंटा गवर्नमेंट के इंजीनियरिंग के फैकल्टी लेक्चर ले रहे हैं आप लोगों के लिए यहाँ पर। उनके पीछे में हमको कितनी हजामत करनी पड़ती है उनको बुलाने के लिए। वो अपने सारे बोर्ड ऑफ स्टडीज की मीटिंग छोड़ देते हैं, डीटी की मीटिंग छोड़ देते हैं, क्योंकि हमने उनको टाइम दिया रहता है और उन्होंने हमको जुबान दी रहती है। मैं अभी अटेंडेंस डाल रहा हूँ फिर से। अभी आप लोग जो 9 लोग हैं वो अटेंडेंस भरेंगे और उन्हीं लोगों की कंसिडर होंगे। देखता हूँ मैं बाकी लोगों को क्या करना है तो। और जब एक्शन ली जाएगी ना तो सब समझ में आएगा कि अच्छा हम तब किया रहता तो अच्छा रहा रहता करके। बराबर 18 रिस्पॉन्स है वहां पर। मैं 18 रिस्पॉन्स है वो सारे के सारे डिलीट करता हूँ मैं अभी। अभी गूगल फॉर्म भरेंगे और लीव करेंगे अटेंडेंस क्लास।